Hey everybody, how you doing? Mr. Palmer here. I hope you're doing well. Uh, this is the video introduction for the weekly assignments for the week of April 27th through May 1st. So happy May Day to you all. Get your lily of the valleys out there ready if you can find them. That's tradition. Um, so what we're going to do this week, if you look at the schedule Monday, you're hopefully looking at this video. Tuesday, you're going to review this PowerPoint. Really, you can probably do both those things in one day. And then we're going to build 3 counters. And these are going to be MSI counters, which are medium scale integration. So just like with our asynchronous unit, someone has taken a bunch of the little individual flip-flops and put them together in a package to market to people. And that package already has a lot of the initial connections hooked up internally, so it makes it easier on the user. And for that, we're going to use 2 synchronous MSI counters. One's the 74LS163 and one is the 74LS193. And our goal for the week is really to complete the counters, but to also be able to compare and contrast them with our other MSI counters that we've built. So the 63 was an asynchronous counter. These 2 are synchronous, which hopefully you're starting to grasp the distinction between those 2. But ultimately, what we're looking for the week, besides the counters, is that you're going to create a Venn diagram to compare and contrast those 3 MSI circuits. So at this point, you can stop watching the video. I'm going to get into a little more in depth for those of you that need it or want it. But at this point, that's the introduction. So if you're continuing on with me, what I want to do now is just show you, kind of take you through this PowerPoint. And not as much as, I normally would or you would, but just give you a brief overview of what's going on here. So this is the 74LS163, and we do have to make the distinction between the 7463 that we were using in the previous lesson. That is, the 6-3 is an asynchronous counter. This is synchronous. The difference being that in a synchronous counter, all of the flip-flops clock inputs come from the same external clocks. And you remember from our previous assignment last week that does require some additional logic, some AND gates and whatnot. However, with the MSI version, that's all been taken care of for you. We see that we have some inputs. We do have some outputs. So this is a 4-bit output. It has a ripple carryout. This would be to indicate when it's resetting, if we were going to cascade these or combine multiple of these together. Say we needed more than count to 15, we would have to add 2 of these together, and we could utilize the ripple carryout to pulse the next clock. We have 2 sets of enables, which we can get into. We have a load, which is connected to all the active low asynchronous presets. And we have a clear, which is connected to the asynchronous resets. We have our clock input, and we have our data inputs. This is how we preset our count. So taking a little further in-depth look here, we can see that all of this are all the connections you do not have to make. That is the advantage right off the bat, is that all of these connections have been made for you already inside the circuit. So this is the internal diagram. We're not going to worry about this too much. Oh, this one's actually important. Counting is enabled. ENT and ENP are both set to logic 1. So for us here, just make sure it's set to 1. We're never really going to utilize them when they're not counting. You could do some interesting things by using combinational logic into these inputs, but for us, let's just make sure that they're always high, ENT and EMP. Because otherwise it would be disabled, the counting. So here's a design for the 163. This is example 1, and this is going to count 0 to 15. Now let's see if we can see why. See if I can zoom in here. All right, great. So don't worry about this component. This is just a wave. This creates this waveform diagram down here. You might be more comfortable using the DC, the binary to hex display, or you can just use binary. Sorry, we're on example 2 for some reason. All right, back to example 1. So this is the full count. We have to power the chip, so VCC goes to 5 volts. We've previously said that ENP and ENT have to go to power if we want it to count, and we do, so that goes to power. And we're not using the active low load or the active low clear, so those go to power as well. We're going to ground the ground. A lot of the chips, some of the chips might not have the ground or VCC. Don't worry about it if they're not there, but if they are there, then ground goes to ground and power goes to power. Make sure you have an external clock going into the clock input, and you do want to ground the other side of that clock. I wouldn't have it at 100 hertz. I'd probably have it at something like 10. We have 4 bits for our output, and this will just give us the straight 0 to 15 full count. This would be where I start. Next thing you're going to want to do is to modify the count in some way. So let's take a look at example 2. Now in example 2, we have a couple of things going on that look different from example 1. The first is that we do have some signals going into our inputs, A, B, C, and D, and I'm going to talk about those. And we also have some signals going into our load. It happens to be a NAND gate, which means when all the inputs are 1s, it will output a 0 once and only once at that moment. So I was talking with someone earlier today, and I was talking to them about cause and effects. So the cause here is going to be the outputs going through combinational logic and into the load or the clear. And the effect is going to be that the number starts counting at whatever we're putting into the inputs on the data inputs here. So the cause, let's look at the cause first. If we look, we have D, which is our 8s, C is our 4, B is our 2, A is our 1. In binary, this ends up being 1101 or 8, 4, and 1, 13. 13 would be the cause. 13 would be when we're triggering our effect, when we want something to happen. Because this is synchronous, I think what you're going to find is you do see that final number. And that's a hint for those of you making the Venn diagrams, is on asynchronous, we do not see that number. We see 1 before it. So we're always programming our count to be 1 after that number, the last number we want to see. But in synchronous, we do see it, I believe. So that's 13. Now, it won't be 13 if you're using the hex display, because that will only go up to 9, and then it's going to switch to hexadecimal. So remember, A is 10, B is 11, C is 12, and D is 13. So D will be the highest you see on that, or in binary 1101. At that moment, 1101, all of these inputs are 1s, which means the NAND gate is finally outputting its 0, which means the load will see its 0. And anytime that active low load sees its 0, it loads in whatever numbers on the data input. So that is our effect. And our effect is going to be to load in a 1 for the 1's place, a 1 for the 2's place, a 0 for the 4's place, and a 0 for the 8's place. So our effect is to load in a 0, 0, 1, 1, or the binary number 3. So the cause is 13, and the effect is 3. So once it gets through that initial count 0 to 13, what I would expect to happen is that that starts back at 3, and from then on it's going to count 3 to 13. So this is a 3 to 13 counter, up counter. And if we look at the notes here, I was correct, which is a good sign that I know what's going on. Now the question is, do you? So ask yourself, well, how could I test myself if I understand this concept? And the easiest way would be to come up with a number sequence that you want it to count to. Let's say, I mean, you don't have to think too far out of the box. This one was 3 to 13. What if we did 4 to 14? You know, if you were able to do that, that would prove that you understand the concept. So let's do that. Let's say that it's a 4 to 14 up counter and make the necessary modifications to do that. After you're done with the 163, then we're going to talk about the 193. Now, the 193 is a little bit more advanced. It looks very similar. The differences I see are that the clear is no longer active low, it's active high, and there's an additional clock input, which is labeled down. So that suggests to me that this might actually have some down counting capabilities. If we look at the other side, we have a borrow out instead of carrying. That's the exact opposite of carrying, and that's what happens when we're counting down or subtracting, is that we're borrowing. So that's why that exists. The internal workings a little bit more complex, but you're not responsible for that. So, just think of this as everything you don't have to do. If clear is set to a logic 1 because it's active high, remember there's no bubble here, so it's an active high. If clear is set to a logic 1, the output, where was that? If clear is set to a logic 1, outputs are immediately cleared. So if you want it to work, make sure that that is not a 1. Make sure it is grounded. Load set to a logic 0, outputs are loaded with the input immediately. This was very similar to our last gate, the 163. So if you don't want it to load anything, make sure it's always a 1. So a little bit different than the last one where it was 1, 1 on those ENT, ENP inputs. This is now 0, 1. If we wanted to do the full count. Don't worry about any of that, and let's take a look at a full count. So this is going to be a down counter, 15 to 0. So no modifications, just going the full extent of the counter. We see load, which is active low, is going to high. We see clear, which is active high, going to ground. We have our clock. It's going into the down clock. The one clock input we're not using is hooked to power. That's a good little tip that we didn't cover yet. And then this will give us the full count, 15 down to 0, at which point we should see the borrow out pulse. So not too difficult, but definitely start there. Once you get that running, then we can modify it. So here's a modified count. Let's see if we can predict what is happening. So first of all, is it an up or down counter? Well, we see our clock going into down, so it's a down counter. It's the same with the cause and effects as before. The cause is coming from here, so we're starting at 15, and we're going to count down until all of these are 1s. Now, all of these will be 1s when this is a 0, this is a 1, this is a 0, and this is a 0. So 0, 0, 1, 0, which is the binary number 2. So 2 is our cause. At that moment, all of these inputs are 1s. For the first time and only time, the NAND gate outputs a 0, and the active low load now sees it's 0 for the one and only time. At that moment, it's going to go and it's going to read whatever data is sitting on these inputs here. So A is the 1's place, that's a 1. B is the 2's place, that's hooked to ground, that's a 0. C is the 4's place, that's a 1, it's hooked to power. And D is the 8's place, that's hooked to 1. So we have 8, 4, and 1, or 13. So this will count 13 to 2, we think. The only question we have is are we going to see 3? Or sorry, are we going to see 2? Or are we going to see one number before 2 since we're counting down 3? And I think with the synchronous, you do always see that final number, but test me on that. It's been a year since I've checked it. But I believe this is a 13 to 2 counter. Let me just check my notes here. So this is actually saying 13 to 3. All right, and that's suggesting that we do not see that final number, which could be a good thing to include in your Venn diagram at the end of the week, if that is true. But go ahead and build this, see if you can get it counting 13 to 3 as stated. Make sure that is true. And then if that's true, modify it. See if you can understand it. You don't have to think too far outside the box. You might want to try 12 to 5 or 12 to 6 or something, but set a goal and then try to build it. the final thing for the week is going to be an up counter. When you go to build your up counter, it's really the NAND gate can't be a NAND gate anymore because if you look at that, or actually, that's fine, but the clock has to go into the up counter is what needs to change there. So play around with that, and as always, it's easier if you're experiencing difficulty just to contact me. But that's the overview for the week. Very brief, but hopefully it's enough to get you going and get you asking me the right questions if you're experiencing difficulty. Hope you're doing well. Hang in there, and I hope to see you soon.